Here we're just going to review the unit where we had identities, where we're proving identities. We also had our sum and difference and double angle identities, where we did those type of circle problems. Applying the identities, we applied the sum and difference and double angles to a small extent in our proofs, and we won't do a lot of that. And we also had our trig equations that we wanted to solve for. Okay, so those are the main areas. So with identities, again, make sure you have some strategies. It's really important that you go over a lot of practice. The more practice you do, the better you get. In fact, most people after they've gone through this unit find this unit relatively easy, where this unit can be very difficult at the very beginning because you have no experience doing it and you haven't developed some strategies. So this one here, one of the strategies we developed was just changing into sine and cos. So sine x, that's going to be sine x over cos x, and that's times 1 over cos x. Here we're going to end up with 1 over sine x cos squared x. Okay, well, the nice thing is we have one fraction. We only want one fraction on this side to make it match. And when we get a common denominator, the denominator matches this one. So what should naturally happen is this should just work itself out. So I'm going to multiply top and bottom by cos squared here, and multiply top and bottom by sine here to get the common denominator, and we end up with sine x times cos squared x. Oh yeah, the numerator is just going to work out to 1, and we have left side equals our right side. Okay, check, it's proved. Here's a double angle problem where we have 1x here, but 2x is here. Well, it's probably much easier to convert 2x into 1x rather than trying to figure out a 2x formula in here. Although, if you look closely enough, you should be able to see that there is actually a 2x formula in there. Okay, so I'm just going to do this. 2 sine x cos x. So at least we have just x's here. Now, I want to generate that, and I notice that I have a common factor of 2 sine x cos x. So I'm going to factor that out. So take that out on this side. So take out the 2, take out a sine x, take out one of the cos x's, and what's left behind? Well, here I'm going to be just left with cos squared. Here I'm going to be left with sine squared. Oh, when I look at that, well, there's my identity of 1, and I end up with 2 sine x cos x equals 2 sine x cos x. Okay, done. Left side equals right side. So we also solved equations. And solving equations, we can't solve for sine, tan, and cos at the same time. This is just not possible. We need to isolate one function at a time. However, the way we get around that is if we can separate these terms in factors equal to 0, each factor itself can be solved independently. So the sine x can be solved in its own equation equal to 0, because if that's equal to 0, that's it, since we have products, 0 times anything is going to solve that equation. For tan x minus 1, well, I just need to find out where tan x equals 1. That will give me a 0 for the tan. For the cosine, I just need to figure out, well, solve that factors, because if this factor equals 0, then the equation again is solved. So if I solve for cos x, I get cos x equals 1/2. Well, then I can just solve these. These happen to be exact values, so sine is equal to 0 here and here. Okay, so x is equal to 0, x is equal to pi. It's going to have a period of 2 pi, so we can do it like that, 2 pi n. If you think of this problem though, we're going to hit the solution every pi, so this is not necessary, but if we want to group this together, we can just say x is equal to n pi, okay, because as we start at n equals 0, n equals 1, n equals 2, etc. Okay, but this is good enough. Okay, we don't need to do that other part, although it looks better and more efficient. tan x equals 1 means the slope is 1. That means we're talking about these two positions here. So x1 is equal to 45 degrees, or pi over 4. x2 is equal to 225, or 5 pi over 4. So again, the same thing's happening here. We can say that they repeat every pi, so I'm just going to write it like this. X is equal to pi over 4 plus n pi, although we could do this plus n2 pi here plus n2 pi here. Okay, this is good enough. This actually is better. The last one, solve for cos x equals 1/2. Cos equals x equals 1/2 here and here. The horizontal is the short side, so x is equal to pi over 3 and negative pi over 3, but I'm going to, just in case they need the positive version of that, I'm going to say that that's going to be the same as 5 pi over 3, which is the same as negative pi over 3. Again, the period is just going to be 2 pi, so I'm just going to go 2 pi times n. Okay, that'll give me all the coterminal angles of theta 1 and theta 2.